So the topic of this talk is the following: to make sure that the code that runs on a PLC behaves correctly. So I'm not going to focus on the hardware or the firmware that's on the PLC, but just on the logic that runs on top of that. And so when is the code correct? We have to give a definition for that, because depending on the people you are talking to, you may get a different understanding of the word correctness. So for instance, if you talk to an end user of the program, he might tell you, yeah, the code you gave me is correct because I ran it for several weeks on my scenarios and it never failed. If you talk to a programmer, he might have a slightly more precise understanding of the word correctness. It might tell you the code is correct because it has passed all the tests. Here we go for another definition of correctness, which is, in our opinion, more precise, which is the following. The code is correct if it is mathematically proven to adhere to some requirements. So we take the requirements of the code, we take the code itself, and we use a tool to check that the requirements are satisfied by the code. So why are we interested in this? Well, because there are several actors that might impair the correctness of the code. One of them you know very well. It's attackers from malicious entities, so like ladder logic bombs, so the injection of some malicious code and the concealment of that in such a way that at some point it will trigger and cause an inconsistency, or the vulnerability exploitation. But we also have to take care of our own problems, so mistakes that we inflict ourselves, which are essentially bugs. Bugs can be caused by incompetence, lack of training, the fact that we work under pressure, so we have to do some urgent quick fix, or outsourcing, or many other sources of bugs. And so what are the countermeasures that we can apply in order to preserve the correctness of our program? I'm going to enumerate some of countermeasures that are meaningful from the point of view of software engineering. So for instance, we can do code review. But code review is a human effort, and as any human effort is subjected to an error. And when you do a code review, you have to enter the mind of the person who has developed the code. And this is not easy. And to support this thesis, I will summon a giant of computer science, Ken Thompson, co-inventor of Unix, that once said, you can't trust code that you did not totally create yourself. Okay, so you can also write tests, but tests depend on the coverage. You may have a lot of tests that cover only a small portion of your code, and that would be ineffective. And there is another problem with testing, that tests can only show the presence of bugs, but not their absence. This is a quote from another giant, Jystra. Okay, so you might also apply some PLC secure coding practices. Fine. But again, this is a manual effort, so you have to convince people to use them. This is not always easy to enforce. What we go for in this talk is another approach, which is model checking, which I will explain in the next few slides. And well, I like to think that these two people would love to see this approach listed in a possible countermeasure for maintaining the correctness of a program. So what is model checking, at least in the way we apply in our experimentation? We take a program, in our case, a Rockwell L5X file, and a query. A query is an expression that is made up on signals that are inside the program that we would like to verify. And the outcome of model checking can be either that he has found a trace. So a trace is a sequence of input values that if we were to replay on the original program, would get the program to satisfy the query. So it would get the program to a state where the query is satisfied. Or model checking can say no trace exists. And when it says so, it means that internally he has developed a proof, a mathematical proof, that can make sure that no possible trace can be ever found on the program in such a way that the query would be satisfied. And how is this magic going to work. I cannot go in the details of the technique because it requires a lot of background in mathematical logic and algorithms. So I will try to explain it with an analogy with a scientific method, which is something that everybody should be familiar with. So in the scientific method, you have a system that you want to study. For instance, two kids running down a slide. And you observe this phenomenon, you make some work with your brain, and you come up with a mathematical model. The mathematical model will capture completely the system under your study. And once you have that, you don't even have to repeat the experiment to understand the system, the original system. It is completely captured by the mathematical model. So you can take a calculator and without having the kids run down the slide, compute the velocity, the acceleration at any point in the slide. With model checking, we do something similar, but with PLC code. So in our case, the system under study will be the PLC code. And we do some automatic translation by means of a computer algorithm into a mathematical model, which I explained in the next slide. And again, with the help of a tool, we will be able to do predictions and calculation on the original program without actually running it. So what is this mathematical model that we will use? It can be explained by this screenshot. This is an actual screenshot taken from the master thesis of Claude Shannon in 1940. It looks like a ladder logic program, but it's not. It's actually an electromechanical circuit, because at that time, ladder logic did not exist. And the observation of Shannon is the following, is that that circuit can be actually translated or maybe captured by the formula that you see at the bottom. So there is a one-to-one correspondence between the behavior of the circuit and the mathematical formula at the bottom. Once you have translated that into the formula, you can apply all the mathematical tricks that are available, theorems, formula rewriting, synthesis, and so on. And therefore, this is really a great contribution. It is turning the art of writing a circuit into the science of analyzing the circuit by means of a mathematical formula. So let me just recap our method. We take a ladder logic program in L5X format. We translate it into a mathematical model following the translation that I showed in the previous slide. And by the way, we are submitting a patent on this translator. Then we take a query. We combine the query and the mathematical model, and we give it into a tool that is called the model checker. And the model checker will either produce a trace, so a set of input values that have to be given to the original ladder logic program in order to satisfy the query, or it will say that no trace can be possibly found. And you won't see all these details in the next slides, but everything is wrapped by our own SDK, which looks like this. Some of you might be familiar with this UPython programming environment. Essentially, it allows you to write Python code and also produce some nice graphics, if you like. So here I'm loading the program that you see in the upper right corner. It's essentially a very stupid program. It's a counter, a handmade counter, okay, that it increases at every cycle of the PLC if the input X is evaluated to true. When the value of the counter reaches the value 10, the coil flag is set to true as well. So let me now run this program. So I have recorded it. And this is what the tool is able to produce. It is able to synthesize a trace where it says essentially that you have to set the variable X every time to true in such a way that the counter in 10 steps will reach the value 10, and therefore the flag can get to the value true as well. Okay, so this is a very simple example. To show something more involved, I will introduce now another example. It's a simple example of an elevator. It's a classical elevator where the cabin can go up and down in 3 stories. There is a motor that can move the elevator up and down. So we have 2 output signals, up motor and down motor, that are able to move the elevator. And there are some buttons. The pink buttons are the buttons that can be used to call the elevator at a particular level. And the yellow boxes are sensors. So the sensor detects whether the elevator is at a particular floor. And we also have some logic to control the cabin doors. So there is a motor to open and close the doors. And there are, again, 2 sensors that are able to understand if the door is open or closed. I have coded this example, and it turns out to have 16 rungs, 10 inputs, 4 outputs, 2 timers, and 9 variables. I have adapted from the website that it's listed at the bottom. OK, so let me show the first application of model checking to this running example. So let's write some requirements that this example should satisfy in order to be correct. So if we really run out of, of ideas, we can, for instance, try to apply the PLC, secure PLC coding guideline number 7, which says, make sure that paired signals are not asserted together. So in our example, we do have paired signals. We have up motor and down motor. So for instance, we can say up motor and down motor must not be true at the same time. This will be our first requirement. Then we also have the requirement for the door. So we don't want the door to be opening and closing at the same time. That will be our second requirement. Then we can add some safety requirement, like while the elevator is moving up, I don't want the door to be opened, because otherwise I will scratch my face against the moving wall. And I don't want the same when the elevator is going down. So these first requirements define something that the elevator must not be doing. We can also define some requirements that say the elevator must be doing something. So we can, for instance, say that eventually the door must be opening, okay? That eventually the door must be closing, that at some point it is possible to start the motor in the up direction and in the down direction. So we have defined 2 kinds of requirements. The red requirements are those for which a trace is not expected out of our system. Because if we were to find a trace, that it would mean that the query would be satisfied. Instead, we don't want the query to be satisfied. We just don't want to find any possible example that would make up motor and down motor asserted at the same time. The blue requirements instead are requirements for which a trace is expected. We want to see an example that would lead to the door to be opening or closing, or the motor going up or down. So again, I have loaded all these requirements into our SDK. And for the first 4, we won't see much. It will say that no trace is expected. And for the other ones, instead, it will produce some counterexample. Now, I will stop on 2 examples. I just have the video run until the end. And then I will. OK, I can just advance. So this is an example where the requirement is satisfied, and it doesn't produce a trace. So our system is correct, because it is never the case that up motor and down motor can be asserted at the same time. If you remember, we have taken this requirement for the PLC coding guideline number 7. So effectively, what we have done, we have proven, we have found a way to automate the checking of rule number 7 in our system. This is another example where instead we were producing a trace for the requirement. So this is an example where down motor is supposed to be activated, and I can readily take this trace and understand what's going on in my system. So in this case, I have the elevator that is at the second floor, because variable at second floor is set to true, and somebody has pushed the button for the first floor, and as an effect, the motor is going down. So how can this requirement and the tool be used? One way is to do one development process that we call requirement-driven development. Maybe some of you will be familiar with the notion of test-driven development. It is a software engineering method where you first develop your tests, and then you develop your program until your tests are satisfied. And here we can do something similar. We can write our requirements first and iterate in the making of the program until all the requirements are satisfied. Another usage for checking the requirements is the classical non-regression. So we have the first version of the program, which satisfies all the requirements, and now I have to produce another version of the program, and if it's not correct, some requirements will not be satisfied. So now I'm showing you this second approach, this non-regression, to defend from an attack. It is a toy attack for a toy example, so nothing very probably interesting in practice, but here it is. So I have taken a rung here that controls the opening of the door, and I have added some more opportunity for the door to get open. And okay, so maybe this is the result of some development. You know, now I didn't make any particular effort in concealing this logic, but you know, maybe mixed up with a lot of other commits for the same for the same you know, implementation. It can be passed unnoticed. But what happens when I run my tool? So the result is the following. This requirement was initially producing no counterexample, no trace, okay? Because it was not supposed to happen. It is not supposed to happen that the door gets open while the elevator is moving up. But now, in the new version of the program, we have gotten a trace. So if we analyze the trace, we can observe the following, that the elevator is initially at the ground floor, and somebody pushes the button to activate the motor to go up. Immediately after the next execution of the cycle of the PLC, we get into the following state, that the up motor is still going up, that the door is opening, but there is also this strange thing that, you know, the cabin is supposed to be at the second floor, which is something that is physically not possible in the original program. But now it's kind of possible because of the little modification that we have done to the program. And this suggests an opportunity for an attacker to actually violate this property here. So if we put something here, some device or some other thing that is able to tamper with the sensor at the second floor, then we could get the violation of the original requirement. So by means of running this algorithm, I am able to discover some potential opportunity for an attacker to violate the requirements of my program. So another application that we can have for these techniques is the so-called equivalence checking. In equivalence checking, we don't actually write the requirements for our program, but rather we focus on a version of the program that we call the golden version. So maybe it is a program that it has been running for years, and it is running fine, and we are very confident that it is correct. And we want to make sure that the new version of the program is actually equivalent to the first one. So how can we do that? Well, instead of defining the requirements and translating the model of the programs, we actually translate both models of the program. And inside the translation, we actually connect the input values, the input signals, to both the golden and the new ladder. And we ask the tool whether these are different or not. So if the two models are the same, then given the same input, you will get the same output. But if the tool is able to find a value for the inputs that will get the output to not agree anymore, then it means that there is a difference in behavior between the previous and the new version of the program. And if we run our tool again, this time, instead of defining some requirements, I actually give as input both the original and the modified program. Then we get, again, to find a difference. So now the difference is on the output open door motor and from the design A and the design B. And it is exactly the same counterexample that we would find, that we found before with the modified attack for the ladder logic. Okay, so what I have shown you is two potential applications of model checking to some logic from, ladder logic from the Rockwell environment. And we have shown the requirement checking, where we define some requirements and we check if they are correct, or equivalence checking, whether we compare two designs for equivalence. What I've done here, I have focused on the ladder logic, but the method can be applied also to the other languages that are available from the standard. You just need to have to provide a translator. I just did the ladder because it's the easiest language to be translated. And from what I've shown here, it's something very easy to do, but it might not be the case, because normally programs are not designed to be, to be modular enough to be analyzed. And sometimes there is no separation between the logic from the rest of the program. And essentially, we need to, in order to apply these techniques in an effective way, we need to define a sort of design for checking paradigms. And this is perfectly in line with the PLC secure coding guideline number 1, where that it suggests to split the code into modules. And yeah, myself, I'm not a PLC programmer. I know how to program PLCs, but I don't do it professionally. So I wish that I could talk to somebody who is more expert than me and maybe have a discussion on what is useful and what is not about the methods I have shown. And perhaps one way to have these techniques applied in practice is to squeeze them inside the available IDEs in such a way that it could be applied transparently by the user without knowing the internals of the various mechanisms that are to be applied under the hood. And okay, it was blocked. And so at Nozomi Networks, we are working to integrate these techniques inside our tool chains in order to have an even higher level of protection for our customers. And that is my last slide. So if there is any question, I'm ready to take them. There is a mic there. Functional block? Yeah. So as I was mentioning in the slide, you need to have a translation from that language to the framework that I made. I made just a translation from ladder, but it is also possible to do with the FBD language as well. Okay. I don't see any other raised hand. Oh, yeah? Yes? Thank you. Thank you. Okay. It is also possible to, tackle other vendors. With the Rockwell format, it's very easy because it's essentially an XML, so it's easy to parse and to modify. Other vendors doesn't have such an easy way to parse the programs that you write in their IDEs.
So how do you kind of see this fitting together besides, you talked about an IDE, but as Nozomi kind of fits into a different space in the marketplace, so kind of how do you see this fitting together with kind of what Nozomi's doing overall?
Yeah, this is something that we are working on, especially the method that okay, now the slides are no longer visible, but the equivalence checking, okay, thank you. The equivalence checking here can be really useful when you notice that on the network there is some upload of a new program. You can run this kind of algorithm and see if you really get the expected result. So if you were intended to modify the logic, or if it was just an accidental or malicious kind of program modification.
So out of curiosity, spinning from that, you've been talking mostly focusing on the actual code, but I was kind of curious, did you guys look into all the kind of applying kind of traditional binary analysis approaches to maybe actual binaries that are being uploaded with the PLC as opposed to the written logic?
Sorry, I didn't get exactly because there is a fan up here and. Yeah.
Sorry, I was curious. Have you guys played around with the idea of looking at the binary files that are uploaded themselves rather than the actual structured text?
Okay.
Or
So binary files is another matter, of course. You would need to reverse engineer them and reconstruct the actual logic. But yeah, that is something also interesting to think about, yeah. Thank you.
Real briefly, does your tool support analysis of custom written AOIs, or is that a feature that needs to be added?
No, this is not actually a tool that we can sell or provide to the user. This is an investigation that we have done. So we have taken our own toy examples and what we have in-house. And it is just a way to prove that these techniques have a future that can be used. And then from this point on, this is a starting point, we will move on and perhaps capture more and more logic from more PLCs, more vendors, and more features.
Thank you.
Thank you. Yes?
Yeah, can you deal with analog values, analog inputs and outputs? Like, can you do some kind of constraint checking?
Yeah, it is possible to deal with them, yes. Because the tool supports floating point logic, and also it has some abstraction to deal with real arithmetic. So this is difficult to do, but it can be done, and well, it's already supported actually.
Oh, cool.
I just don't have examples.
I was going to ask if you had like timing examples, how long that takes usually.
Yeah, so in that case, you would have to do some sort of abstraction and say, my timer, take slices of this timer and say, 100 iterations are actually compacted to some unit and, some one-time stamp or something like that. But yeah, it's something difficult, but it can be worked out. Cool. Thank you. Okay, I guess the time is over. Thank you very much for your attention, and see you again.